Consider the polynomial p of x is equal to 2x cubed plus 7x squared plus x minus 10. For part A, we want to use the rational root theorem to identify one rational linear factor of p of x. So when we use the rational root theorem, we're interested in two of the terms in the polynomial. The first is the leading term, and then we consider its coefficient, which will be 2 in this case. So remember that the leading term has the variable x raised to the highest power. We're also interested in the constant term, which is negative 10 for p of x. Our rational root theorem states that possible factors are given by plus or minus the factors of negative 10 divided by the factors of 2. So that is equal to plus or minus the factors of 10, which are 1, 2, 5, and 10, divided by the factors of 2, which are 1 and 2. So using that information, we can list out the possible factors, which will be 1 divided by 1 gives 1, and then we also have negative 1. Then we have 2 divided by 1, and also negative 2, and this continues. So now we have a list of all the possible factors for p of x. We're going to test the non-integer factors of p of x in this example. So the first one we're going to do is test p of 1/2. And if you evaluate that, you find that that is equal to negative 15 divided by 2. Next, we're going to test p of negative 1/2, which is equal to negative 9. So we move on and we're going to test p of 5 divided by 2. And that is equal to 135 divided by 2. So it is also not a linear factor. And next, we're going to test p of negative 5 divided by 2. And that is equal to 0. So this gives us that x equals negative 5 divided by 2 sends the polynomial equal to 0. So if we rearrange that, we find that 2x plus 5 equals 0, which means that 2x plus 5 is a linear factor of p of x. And we reached that conclusion using the rational root theorem and the factor and remainder theorem. So for part B, we want to use long or synthetic division to divide p of x by the linear factor identified in part A. So the linear factor was 2x plus 5, and if we solve that equal to 0, we found that x is equal to negative 5 divided by 2. And now in this example, we're going to use synthetic division to divide this polynomial. So we start with our negative 5 divided by 2, and that goes into this position. So negative 5 divided by 2 sits here. And then the coefficients of p of x, which are 2, 7, 1, and negative 10, sit in these positions here. So the first thing we're going to do is add down the first column. So we have 2 plus 0 gives 2. And the next thing we do is multiply negative 5 on 2 by 2, and that will give us negative 5. And then we add down the second column, which will give 5 plus negative 5, which will equal 2. Then we once again multiply the negative 5 on 2 by this 2, and that will give negative 5. Then adding along the next column, we find that 1 plus negative 5 is negative 4. And then we repeat the multiplication again, so we have minus 5 on 2 times by negative 4, and that will give us positive 10. And then we add down the final column, which gives negative 10 plus 10, which is 0. So we have a remainder of 0, which means that the 2x plus 5 perfectly divides the polynomial p of x. So because the divisor that we had a coefficient of x that was not equal to 1, we have an extra step involved. So what we need to do is we need to divide every one of these numbers by the coefficient of x in the divisor, which is the 2 here, before we find what the quotient is for this synthetic division. So the 2 divided by 2 goes to 1, so that's just x squared. And we have 2 divided by 2, which will just give plus x, so the coefficients of both those terms have been 1. And then the coefficient of the constant, or the constant term, is negative 4 divided by 2, which is just negative 2. So just a reminder that that was 2x cubed. So down the bottom of that column, we find that it is 1x squared. Similarly, this was 7x squared. So at the bottom of that column, we just have 1 less power, which is just x. And where this was plus x, we just have a constant at the bottom of that column. So we have found that when we divide p of x by 2x plus 5, the quotient is x squared plus x minus 2. For part C, we want to fully factorize the polynomial p of x. So p of x can be written as the multiplication of the divisor, which was 2x plus 5, multiplied by the quotient that we found, which is x squared plus x minus 2. So to fully factorize that polynomial, we now need to factorize the quadratic. So what we do is we look for the factors of negative 2, and they will be negative 1 and 2, and 1 and negative 2. And we want these to sum up to be the coefficient of the b term, which is plus 1. So when we add these two together, we get plus 1. So this is the pair of numbers that we can use to factorize that quadratic. So p of x can be written as 2x plus 5 multiplied by x minus 1 times x plus 2, where the minus 1 here is that minus 1 there, and this 2 is that 2 there. So that is the fully factorized form of p of x. For part D, we're going to use the factorized form of p of x found above to solve the equation p of x is equal to 0. So if p of x is equal to 0, that's the same as 2x plus 5 multiplied by x minus 1 multiplied by x plus 2 being equal to 0. So using the null factor law, we can say that 2x plus 5 must equal 0, or x minus 1 equals 0, or x plus 2 is equal to 0. Each of these is just a linear equation, so we solve it by undoing. So we subtract 5 from both sides of this equation, and that gives us 2x is equal to negative 5. And then dividing both sides of the equation by 2, we'll get x by itself. And we find that x is equal to negative 5 divided by 2. For x minus 1 equals 0, we'll add 1 to both sides of the equation, and that will give us x is equal to 1 as a solution. And finally, we have x plus 2 is equal to 0, so we're going to subtract 2 from both sides of that equation, and we find that x equals negative 2 is the third solution to that equation. So we have 1, 2, 3 solutions that satisfy p of x is equal to 0.